אז לפני שאני מתחילה, אני רוצה לחלק פליירים לכנס היסטור שמתקיים ב-IBM חיפה שבוע הבא. אתם כולכם מוזמנים. אוקיי, אז אני אדבר על ארכיטקטורה גם ל-Ingestion של דאטה וגם של Analytics. ב-Internet of Things. כן, אז דמי הציעה שאני יכולה לדבר באנגלית, אולי זה יותר טוב להקלטה. I prefer speaking in English. So does anyone mind if I speak in English?
No, I don't think so.
Okay. Well, really Australian, but if you don't understand my accent, just ask me to repeat myself. Okay.
It looks academic.
Or something.
Yeah.
Speaker notes.
Oh, thank you. Yes, thank you. Okay, so I'm this talk's going to be a little bit more high level than the previous one, but just feel free to ask questions and we can go as deep as you like. So what's the Internet of Things? Probably everyone's familiar with it by now. We have physical objects which contain chips, sensors inside, and they capture and communicate all kinds of data. And they're linked through networks to the internet. Advanced things have actuators, which means that they can actually take action. So they could be a lock on your door and you could give them a command to lock or to open. And so what's all the fuss about? Because sensors have been around for a very long time, way back in when rockets were sent to the moon and so on. So, why now is there all this buzz on the Internet of Things? So the reason is an economic one. The price of sensors has fallen, cost of bandwidth has decreased, and all of these reasons here are economic, and this is what is causing the multiplicity today of the number of devices that actually exist and are communicating data to clouds, to the internet. So, and I actually, this slide is a little bit old, but I went and checked and found a prediction even just from last year that 2020 will see 30 billion devices connected. So this is more than 4 times the population on the planet. And all these devices are continually generating data, so this is really how we're getting such big data today and in the future. So, way back where this was the way to get data into computer systems, and then we evolved to, okay, let's type things in, but now this is the way to get big data by devices connected to the internet. So I want to argue that we're all here interested in big data, but the biggest big data is Internet of Things data. And I'm cheating a little bit because you can say that, okay, media is also Internet of Things because we have cameras everywhere and they're sending media. Maybe the recording of this talk can be considered Internet of Things data. But so I'm trying to say that this is the most interesting big data use case, or it's not really one use case, but family of use cases. So now that's just the introduction, and now I'm going to talk about a real life use case that we worked on with Madrid Council. In the context of a European-funded research project called Cosmos. And Madrid Council today has control rooms where they have staff staring at cameras all day long, and traffic engineers need to pick up on any traffic issues and then take action. Maybe, call ambulances or change traffic light behavior or, do something. And the question is, can we help traffic engineers be more efficient in their work by doing some of the work automatically? So Madrid Council has around 3,000 sensors located in different places in the city. They send data, periodically send data. Data could be speed, in traffic intensity, and so on. And our approach here is to use this data to help traffic engineers alert them if there's any unusual patterns, and they can spend their time doing more, critical things. Okay. So what I'm going to talk about next is, what's a kind of good cloud architecture for this kind of problem. And we're talking in general about IoT use cases. The particular one here is traffic in Madrid, but could be other IoT problems. So this is my first attempt. Okay, so we have Internet of Things. This is traffic sensors in Madrid. They're sending data to a message broker. It could be something like Kafka, for example. And then we have some kind of event processing framework. Could be Spark streaming. It could be some kind of complex event processing engine, which is making some decisions depending on the data that's coming in, and then taking some action, maybe automatically calling an ambulance or changing traffic light behavior. Okay, so this can work, okay, but I think do you agree there's something missing here? What's the? I mean, this is a nice, simple approach, but what's missing? Any ideas? Management. Analytics, yes. And before we can do any analytics, what do we need to have?
Data stores.
Right, storing data. So we're missing history. We're not recording any history of what's happened in the past. And repeating what the previous speaker did by having these quotes from a couple of 100 years ago. Those who cannot remember the past are condemned to repeat it. So if we don't know the history of traffic in Madrid, then we're not going to be able to do anything intelligent at all. So let's extend the architecture to record history. So this is more work, right? This means we're going to have to do a lot of homework. All these purple flows, the batch flows, they're all homework now that we have to do. So we have to ingest the data to some kind of data storage framework. We have to be able to retrieve the data with some kind of analytics framework and do some kind of machine learning. And then that machine learning can, learn something intelligent and tell the event processing framework what to do. So this is a very generic picture of, we call this the hut architecture because it looks a little bit like a hut, a house. And this is the same architecture with certain choices of open source tools. So here we Madrid Council is publishing their data from the census to as a web service, so we're pulling that data using Node-RED. It's not necessarily the best way to do this in general, but that's what we use. Kafka is good as a message hub.
Can I ask a question? What's the difference between this architecture and Lambda architecture? It's
Right,
the same in my eyes.
So this architecture is I think more simple than Lambda architecture. Lambda architecture is known to be quite complex, and it has slightly different motivations. This architecture, what's nice about it is it's all the different pieces and working parts.
Dangerous chairs.
אני חושב שהייתה כולה, לא? לא חשבתי שטל סלימוביץ' יעשה את זה.
Everybody's alive. It's okay.
זה אמור להתקלבי.
אני יודע שקראת לו נאצי.
דמי? האמת שזה בוא נכפת לי. סליחה.
Pandemic, okay.
אני מצטער, מה ניסיתי? I didn't try to steal your thunder.
So the question was, what's the difference between this and Lambda architecture? So Lambda architecture, you have the batch layer and you have the serving layer, and they both have to kind of work in parallel and make sure. So this, the attempt here is for this kind of application to do something which is more straightforward. Okay, so I'm gonna go in a little bit more into detail about the different pieces here, but here we have object storage, OpenStack Swift, which is one kind of object storage is open source. Other kinds are Amazon S3 or Google Cloud Storage, so on. And then we're using Spark for analytics, and we in particular used a complex event processing engine for the real-time behavior. Okay, so in our research at IBM, we are focusing on two of the sides of this hut. One is ingestion and the other is analytics. So they're basically two sides of the same coin in a way, because when you ingest the data, you want to ingest it in a way that analytics is going to work well on it later. So in terms of the object sizes, you use the data format to use what metadata do you generate, the way you partition the data. All of these are going to affect you when you ingest the data and also when you analyze it later on. So I'll talk first about ingestion, then about analytics after that. And they are kind of closely connected. So first of all, are people here familiar with Kafka? So I won't dwell on it too much, but we're using Kafka as a data hub. You can kind of multiplex nicely with it, so you have a lot of different data sources coming in, and you can export two different data sources. So you might export your whole data set to a database and in parallel export the whole data set to object storage. And then you can use the database for your recent data, and you might kind of keep the whole data set in object storage so that you have a long history of data. Secor, I'm not sure if people are familiar with, but it's open source tool that takes data from Kafka, aggregates it or collects it into objects and uploads it into object storage. And we extended Secor to support OpenStack Swift and contributed that back to Secor. These days, if people are really using Kafka, you might have heard of Kafka Connect, and these days Kafka Connect is probably the way to go to connect things like Kafka and object storage. So IBM has a Kafka service called Message Hub, which is part of the IBM Bluemix platform.
What is DashDB?
DashDB is an IBM Cloud database.
That can pull data from Kafka directly?
No, just like with any database, you would have a connector which pulls the data from Kafka and puts it into the database.
this project?
What I'm talking about?
Yeah.
What I'm talking about is research work. So we're a small team of people who have been working on various parts of it. So we're using open source tools. Obviously, but the things we did, for example, was extending Secure to handle OpenStack Swift, and there's some other extensions that I'll mention as well. So by building this architecture and developing this solution, we found some pieces that needed to be extended. But at the beginning, the first slide, it had a list of people joint work with, and some of them were actually not from IBM, but no. Okay. Okay, so how familiar are people with object storage? Amazon S3, OpenStack Swift. I'll just talk about it a little bit. So maybe put your hand up if you're really familiar with object storage. Okay, so not everybody. So what object storage is really good for is very high capacity, widely scalable storage at low cost. So I think the previous speaker talked about using Amazon S3, that's one example. And data there is written once and not modified. If you want to change your object, you have to rewrite it completely. You can't append to the end of an object. You can't update an object. You can update the metadata of an object, okay? There's no rename operation at all. So you want to rename all your objects, you have to rewrite your entire data set. That's usually not feasible. One thing you can do though is you can go to a particular offset of an object and say, okay, just give me these bytes from this offset to this offset. But that's about the fanciest thing you can do. So you access object storage through a RESTful API, so it's really built for cloud. And it has a flat namespace, so none of these directory hierarchies that you have in file systems. Just a totally flat namespace. You usually have something called buckets or containers, so you can put a bunch of objects into a bucket or a container, but that's it, no buckets of buckets. So IBM has a software object store based on OpenStack Swift, and more recently has something called IBM Cloud Object Storage, which supports the S3 and Swift interfaces and works on-prem and cloud. Okay, are people familiar with Parquet format? Okay, some are, not everybody, so I'll just talk a little bit about that. So think of Parquet as a data format like JSON or CSV, and the good thing, it's very good for batch analytics with Spark. So if you want to put your data in object storage and then do batch analytics on it, then Parquet is a good format to use. And couple of reasons. Firstly, it's column-based, so all the data is stored column by column. And that's really good for two reasons. One is for Internet of Things data. Each column could, one column could be temperatures, another column could be geospatial locations, and each column, if it's all stored together, is going to compress much better. That's one reason. The other reason is if you have a data set with, say, 100 columns and you may only need 5 of them, if they're all stored contiguously, then you can just retrieve those 5 columns. As I said before, with object storage, you can say, okay, get me this offset to this offset. So if that column is all stored contiguously between those 2 offsets, you can say, okay, just bring me that column of data. You don't have to read the whole object in that case. So that's why Parquet is a good thing. Elasticsearch people probably familiar.
Question. So
Yeah.
if I'm working with Spark and S3 and Parquet,
Yeah,
and I'm filtering specific column,
yeah.
is it smart enough to not fetch all the data and just
Yeah.
get the range of offset
Yes.
it needs to do?
Yes, the way Parquet works, good you asked that.
Working with S3.
Yeah.
Yes.
Yes, the way Parquet works is that it has a footer, and a lot of metadata is stored at the footer. For example, it says column temperatures goes from this offset to this offset. And so with Spark, if you say select temperature from my RDD, it will know to go to the end. It will have to make a REST request to read the footer. Once it gets
Footer,
that,
not the full
yeah,
object.
first it has to read the footer, but in order to know where to go, and then it will read the columns that you need. But so it will require more than one REST request, but it does know how to do that. Okay, Elasticsearch, people probably heard of it before. You can think of it as a NoSQL data store, but it's really a search engine. You can use it to store JSON objects and then search for them. So object storage, I actually mentioned that all objects have metadata, and you can actually rewrite the metadata even if you can't rewrite the object. And we want to use Elasticsearch to store and index the metadata. So then we can go ahead and search for all objects with certain metadata. And I haven't really told you why we want to do that yet, so I will tell you that very soon. Okay, so this is just to kind of recap the ingestion flow. So we're kind of missing here the sensors, but the sensors are sending, say we have Node-RED pulling sensor data out and pushing it into Kafka. And then we're using the Secure connector to pull data out of Kafka and push it as objects into Swift. It's going to push it into Swift in Parquet format, and metadata is going to get pushed into Elasticsearch. Okay, so now I'm going to explain why we want to store metadata in Elasticsearch. What metadata do we want to put in there? So what we're doing is that, just say we've got traffic data here. Now, one of the queries that the analytics people we were working with wanted to do, they wanted to analyze rush hour traffic, say for the last year. They wanted to say, okay, get me all the rush hour traffic data we have. So what we wanted was to be able to tell whether a certain object was a rush hour object or not. Even if it just overlapped rush hour, we'll say, okay, that's a rush hour object, we need to get that one. But if there was an object that was from the middle of the day, then that object is really not relevant to a rush hour query. So we don't even have to pull that one out of object storage. And if we have that information in the metadata, then we can quickly work out that maybe only 5% of the objects have to be retrieved for a certain query. So what we did was, for certain columns that we chose as being appropriate, we stored minimum and maximum in the metadata for the objects. So just say we had traffic intensity. We have a certain object which might have, say, 10,000 records, and we stored the minimum and maximum traffic intensity for that object. And for the rush hour query, we want to do that on time of day. So I think I'm going to have an example of that in a minute. Yeah, here it is. So we have a time of day piece of metadata, and we're storing the minimum and maximum time of day for each object. So here, this object has data from 12:32 to 1:27. So definitely not relevant to rush hour query. So we just know we don't have to read this one from object storage. Yeah,
If
no,
I'm
that's-
asking too much questions. So
no problem.
אם זה מפריע למישהו. Why Elasticsearch? Because it's not a search as I see it. It's like you can index it as a schema. You know the schema had before. You don't need dynamic schema. You don't have text. Why Elasticsearch? Why not another?
Right, it's true.
Why not MySQL?
Yeah, Elasticsearch is very good at free text and things like that.
Why?
We could have used another tool. We wanted some kind of index.
You have it in MySQL, for example.
Right, we could have used CloudEnt or Mongo or other tools as well. So this talk is really more about general architecture, and we're even I wouldn't really. That's why at the beginning the hut didn't have Elasticsearch. It didn't have any choice of tools on it. You could mix and match.
It's always a trade-off. I
Right.
just want to see if I'm missing something and maybe
Right.
I can learn something.
So we may also. Pardon?
Field names were dynamic or like it was the fixed schema all the time?
Right, so you can, it is possible, in the Madrid traffic situation the schema was fixed, but in other applications the schema may vary more over time. Elasticsearch suited us pretty well. It's a good tool, but I agree that other tools could work well as well.
We detect evolved all the time, right? So we could just imagine there would be more people that we could
Right, but yeah, of course.
start using.
Right, index information is added all the time. Okay, so now I'm going to switch to talking more about analytics in a moment. And so why are we storing the data in object storage? Well, it's highly scalable and elastic, and we're talking about Internet of Things data. So even if we talk about the specific Madrid Council use case, maybe that on its own is not huge data, but in general we want to capture Internet of Things use cases, so we want it to be highly scalable and low cost. We talked about what you can't do with object storage. And just want to point out that, these days analytics and storage are totally separate microservices. Once upon a time with Hadoop, it used not to be like that, and there was all this talk about locality and making sure that the compute was close to the storage. That's not fashionable these days. It's not considered practical. So one of the advantages of having separately managed microservices is each one can scale independently, can be configured independently for its own needs, independently of the other services. But it brings us with a problem that in order to do our analytics in Spark directly on data in object storage, we have to ship data from object storage to Spark, and obviously we want the amount of data we ship to be minimal, and that's the whole reason why we're using this metadata approach. We want not to ship those objects that we don't have to. So just to talk a little bit about how in object storage this kind of data is typically organized. So as I said, namespaces are flat. So why do we see a picture like this? This looks like a hierarchical file system, right? It's not. It's just these long names with slashes in them. And the slashes can represent some kind of hierarchy, but the point of view of object storage, there's no hierarchy here. But it's important to know that Spark SQL actually knows how to look at these names and do something with them. So I don't know if people are familiar with this, but setting out the objects in this way is kind of naming convention that Hive uses, for example. So once the objects are, once this naming convention is used, then this DT value here is date is considered as a column of the data and can be queried. And once that happens, if we have a query on date that asks for all data on the 14th of September, Spark will know just to retrieve the top objects here and will disregard the bottom objects. Okay, so that is today the most common way to restrict yourself and not bring the whole data set from object storage, but just bring a fraction of it. Okay, but that's great, that's incredibly important, but why is that not enough? Okay, well, that approach is limited. Only one hierarchy is possible. It's like a database, you can only have one primary key. There's no secondary keys here. You can't change the hierarchy without renaming all your objects, and as I said before, object storage has no rename operation, so that means renaming your whole data set, and that's impossible in practical terms. You can only partition according to attributes with discrete types, like, for example, male, female, date, age, and so on. It doesn't work well for timestamps, arbitrary floating point numbers like temperatures, pressures, and so on, which is pretty common in Internet of Things data. And if you have a really deep hierarchy because you're trying to push all the columns into your object names, then you're going to end up with these tiny objects, and that's not good for analytics performance. Okay, so that's why we are proposing this approach of, in addition, we're saying use this high style partitioning, everybody does, but in addition to that, let's store metadata and use that to further filter which objects we need to retrieve from Spark. So, for example, store minimum and maximum values. So in Madrid, traffic, the analytics people we were working with wanted to analyze the morning traffic, and we found that we reduced the number of Swift requests down to by around 20 times. Okay, so we didn't focus on this at IBM, but the partners that we were working with looked at the machine learning side of things, so just to talk about that really briefly. So basically they were trying to learn between normal and abnormal traffic, and that really depends on the context. And this is the whole reason why we needed to store the data in the first place and use the history and analyze it. Because if you're looking at a certain intersection and at a certain time of day, say, it could be a busy city intersection in rush hour, the traffic is going to be totally different from a country highway in the middle of the night. So basically they split the data into, each sensor, they built a model per sensor, and for each sensor they split the data into different time periods, one for morning, one for afternoon, one for evening, and so on. And then they learn what is the normal behavior for that sensor in that time period. And once that was known, then they could understand in future whether traffic is normal for that particular location and time period, or whether it's unusual, something weird is happening, something bad maybe is happening. And then they can alert traffic engineers to this unusual situation, like an anomaly. Okay. So basically that, I'm talking about that just to show why all this history is important. And actually a machine can probably do a better job than a new traffic employee who's just been hired, doesn't know anything about traffic in the city, doesn't know which intersections should behave in which way. this system has all the history, has learned what's the normal patterns and can help people. Okay, so we implemented this on the IBM Bluemix platform. The IBM Bluemix platform has a Kafka service called Message Hub, Spark service, and object storage service. We were participating in development of the object storage bridge, which today is in production and connects between the Message Hub service and the object storage service. This is a graphical interface based on Freeboard. So all these pieces work in the Bluemix platform. This is just showing how to create a bridge, for example. So I just want to show you a demo. Okay, so what we're seeing here is the Bluemix platform, different services. We jump to the node red. These are our flows. They're pulling data out of the Madrid traffic web service and pushing into Kafka. This is Kafka here, and this is, well, that was the machine learning. This is the user interface. We see traffic here, different speeds and intensities, and we haven't done any machine learning, so there was no thresholds there. This is Message Hub, which is the Kafka service. Grafana, we see data consumed from Kafka. This is the rate that the data is coming in from Kafka into object storage. This is the log, so you see a bridge was created here. We're just looking at the object storage bridge. A bridge was created. This is information about that bridge in the logs. This is object storage. We see the naming convention used for partitioning according to dates. We have a new object roughly every 15 minutes here. So this is the object storage service on Bluemix. So now we're going to page through the objects and take a look at what a particular object looks like. It's going to be a bunch of JSON records. This particular demo we're seeing JSON data, not Parquet data that I did talk about before. So we're going to see a bunch of Madrid traffic records. That this is intensity in Spanish, intensidad. Velocidad is velocity, so I got to learn some Spanish. So yeah, this is one object. And this is our notebook in the data science experience, which is running the analytics. So what this notebook does is it calculates thresholds. Once you go over those thresholds, then we know the traffic is abnormal. So it's generating thresholds both for speed and intensity. So it's going through the different sensors, and for each sensor it's generating different thresholds. So here we got a threshold 7, 10, and 33 for intensity and speed. And then the next sensor, we have different thresholds. So here we're just showing 3 sensors because that's what we're showing in the user interface. So you see now we have thresholds. So far everything's normal, so no scary lights are showing up. But here later on we have an abnormal state where well, now it's all cleared up, but previously we had an abnormal state. So once you have that abnormal state, you could connect it to some other system which takes some action. Yeah, that's the end of the demo. So I think I just have one last slide to wrap up. So just to wrap up, Madrid traffic is one example of an Internet of Things application, but very similar architecture could be used for many different IoT apps. And the whole focus here was on how to use open source tools and put them together in order to run a scalable application that can deal with big data and work efficiently. Yeah, so in IBM we have been focusing on this because we want to understand how to put the different pieces together, how the microservices should work together nicely, so that on IBM platforms things work smoothly and applications can be pieced together like pieces of a puzzle. Okay, questions?
Did you find interesting insight from the machine learning?
Yeah, I'm as I said, we were focusing in IBM more on the ingestion side and the analytics side, so it was the University of Surrey team that was doing the machine learning, and I can tell you a bit more about what they did, but I'm not really the right person to talk about the insights that they learned from that. Other questions?
Thank you very much.
Okay.